previous lecture, we derived equation of motion, and that equation of motion was derived with reference to descent trajectory. Means how the particles are traveling at a displacement with respect to descent trajectory, and what the trajectory of these particles are making an angle with respect to descent trajectory. In this manner, we derived equation of motion, and that equation of motion was under the dipolar magnetic field and quadrupolar magnetic field. Dipolar magnetic field means a constant magnetic field over a space, and quadrupolar magnetic field means magnetic field has some gradient over the space. Under these magnetic field configuration, we obtain the equation of motion, and that is the second order differential equation. Now we will solve it by one of the methods known as matrix method. This is a very powerful method which provides a tool to calculate the trajectory of particles from each of the magnetic elements. So trajectory from entire optics can be computed using this matrix method. So in this lecture we will see this. Now this is a equation of motion in the horizontal plane, and this is the equation of motion in the vertical plane. Here you can see these equations is much more like the equation of simple harmonic oscillator. However, there are subtle differences. What are those differences? Which we will see here. Here in this equation, Kx is basically 1 by rho square plus gradient of the magnetic field normalized by magnetic rigidity. Normalization by magnetic rigidity actually makes our calculation energy independent. So everywhere in accelerator physics you will see that formulation have been normalized by the magnetic rigidity. Similarly, in the vertical plane we have Ky, the gradient in the magnetic field normalized by the magnetic rigidity. However, there is a minus sign, means gradient in the horizontal plane has the opposite effect than the vertical plane. So in horizontal plane, if gradient is providing a focusing, then in vertical plane this gradient will provide the defocusing, which we have seen during the study of the quadrupole magnet. And in horizontal plane you will see an additional term of 1 by rho square. Why this is an additional term? Because we assume that the bending is taking place in horizontal plane. Means we are making our accelerator in which design trajectory is completely in the horizontal plane. So this is our assumption, and we are under this assumption, this 1 by rho square appears only in the horizontal equation of motion. So now we will solve these equation of motion using some method. In accelerators we use different kind of magnets for different purposes. Now you have learned that the dipole magnet is used to decide the descent trajectory, how much curvature we have to produce, where we have to send the beam, and that design orbit is decided by the arrangement of dipole magnets. So dipole magnets basically decides the design trajectory. So we can say in accelerators, dipole magnets this design decides the design path or trajectory or orbit. And what the quadrupole magnet does? Quadrupole magnet does the confinement of the beam around this design trajectory, which is decided by the dipole magnets. So quadrupole magnet is used for focusing of the charged particles. And each of these magnet, if we are assuming pure dipole magnet means B constant, and quadrupole magnet, it means it has only gradient part in the magnetic field, means it has G, which is del By by del X. So these magnets have different K in the equation of motion. So in the equation of motion for the dipole magnet, if this is pure dipole magnet, means without any gradient, then we will not have any gradient related part in the K for the dipole magnet. And if it is a pure quadrupole magnet, then we will not have any curvature related part in the equation of motion. So each of these magnets have their own value of K. So for each of these magnets we have different equation of motion, means we have different K and we have different equation of motion. So again we see, now first, the simplest structure in accelerator is the drift space. Drift space means a vacuum chamber connecting a straight connecting two magnets or 2 points with a straight line, means there is no magnetic field over this region and particle goes straight without feeling any force. So any trajectory which is going, it will go on its course in the drift space, means drift space has no K. So in drift space, in horizontal plane and in vertical plane, in both the cases we have Kx and Ky 0. So for the drift space we have very simple equation of motion, that is d2x by ds square is 0, and similarly d2y by ds square is also 0. This is basically a differential equation showing the straight line. In the dipole magnet, as we already discussed, that curvature related part will be there. So in dipole magnet, in the horizontal plane we have K is equal to 1 by rho square plus gradient related part. However, we are considering pure dipole magnet, means no gradient, so Kx will consist of only 1 by rho naught square. So Kx is equal to only 1 by rho naught square. Now in the vertical plane, in a dipole magnet, there is only contribution from the gradient part in the K, and as we are assuming that no gradient is present in the dipole magnet, so Ky will be 0 in this pure dipole magnetic field. Now in the quadrupole magnet, curvature related part will be 0, so only gradient related part will be in the Kx, and in Ky also only gradient related part will be there. However, these gradients are opposite to each other in sign in the equation of motion. And in the last, a combination of dipole and quadrupole may occur, which we have seen in our course of weak focusing, that if a dipole magnet has some gradient, it can produce a curvature as well as focusing. So this type of magnet, which is a dipole with some gradient, is known as synchrotron magnet. In this kind of magnet, we have curvature as well as gradient effect both. So Kx will consist of curvature part as well as gradient part. This is the case. And in Ky we already have only gradient part. Now again here you can see, by introducing the gradient, actually you are introducing the quadrupolar component in the magnetic field. So if gradient part is producing some positive effect in the horizontal plane, it will produce some negative effect in the vertical plane. Means if gradient is introduced in such a way that if it is producing focusing effect in the horizontal plane, then it will produce the defocusing effect in the vertical plane, and vice versa. Now in accelerator, even a simple optics, we have arrangement of some magnets, and we can see that In actual optics of charged particles, we can have some quadrupole. Suppose this is a quadrupole Q. Then some drift space, and then again there may be a dipole magnet which bends the trajectory in the desired way. So this is a dipole magnet, and then there may be again a drift space, means no magnetic element, then again a quadrupole, and like this. So now if we consider here the value of K in our equation of motion, you can see that this quadrupole, you can say this is the quadrupole 1. So it has its own K value, Kx, which depends on the gradient of this quadrupole magnet. Then this is the drift space. Here you will have K2, you can say this is 0. Then a dipole magnet, it will have its own K. In the pure dipolar field, it will have only curvature effect in this K, and in vertical plane the K will be 0 for such kind of magnet. Then again you can say this is a K3. Then again a drift space, so you can say again K4, which is again 0. And another quadrupole, you can say this quadrupole is Q2. This may have the strength different from the K1, so it may have its own strength K5, and like this. And this optic axis in our coordinate system is designated by S. So we can see that the K varies over S. When K varies over S, actual our differential equation we can write explicitly in this manner, where K is shown as a function of S. Means K is a function of S, and this is the starking difference of this equation with that of the equation of simple harmonic oscillator. In simple harmonic oscillator, we have d2x by dt square plus omega square x is equal to 0. Here omega square is a constant for a given oscillator. Here you can say this is not a constant, instead it depends on the independent parameter S. So how we can solve this equation? In this class, we will see that we can break Ks or K as a function of S in the pieces, where we can make this K independent to S, and then we can solve the equation. How we can do this? We see now. Suppose there is a quadrupole magnet, and then there is a drift, and there is another, you can say dipole magnet or like that. Quadrupole, then drift, and then dipole magnet. Now as we have said that this has its own K value. So within this quadrupole length, you can say we have K as a constant. After this quadrupole, K becomes 0, but within the drift space length, this is again a constant quantity, K is equal to 0. Then in dipole, if dipole is of sector type magnet and there is no gradient, then it has certain K decided by its radius of curvature. Again, within the body of this magnet, this K will be constant. So within each magnet, K has its constant value. So within each magnet, our equation will be exactly similar to the equation of simple harmonic oscillator. And when in a single magnet, we have equation like the simple harmonic oscillator, so we can write down easily the solution of this simple harmonic oscillator equation, as we know that xs is equal to a cos root ks plus b sin root ks, and these a and b can be decided by initial conditions. So this will be the solution of equation of motion when we consider as a constant K inside a single magnet. Its derivative, because we are going to solve second order differential equation. So we need two initial conditions. So first initial condition can be the position itself, and the second initial condition will be the derivative of this x prime, which shows the angle. X prime is dx by ds, and it represents the angle in the paraxial approximation, as we have seen. So differentiation of this quantity will give you root k sine root ks with minus sign, which is written here, and root k cos root ks, which is written here. So this is the derivative of the first equation, which gives you the x prime. Now at the initial point we can consider as the beginning point of the magnet, and at that beginning point you can say S is equal to S0. It is our beginning point when the particle enters inside the magnet and starts feeling the force designated by this K. So at that location we can have at the beginning x is equal to x0 and x prime is equal to x0 prime. These are our initial conditions at s is equal to s0 at the beginning of the magnet. So we can put x0 value in this equation. So we will get x0 is equal to a cos root k s0 plus b sine root k s0. And similarly we can put x0 prime in this equation. So we will get x prime 0 is equal to minus a root k sine root k s0 plus b root k cos root k s0. Here now, because we are solving a given magnet, equation of motion in the given magnet, so root k is known to us. S0 is the initial point of the magnet from where the we want to solve from where our particle will trace out its path inside the magnet. So this is the starting point of particle trajectory in the magnet. x0 and x0 prime, these are initial condition which we know. So now in these two equations there are two unknowns. One is a and another is b. So we have two equations, two variables. We can solve it very easily. So solution will give you a as a function of initial conditions x0 cos root ks minus x0 prime root k sine root ks. And similarly we will get the b, and b is equal to x0 sine root ks0 plus x0 prime root k cos root ks. So now we have a and b as a function of initial condition. So if we put these a and b value in our solution, we will get the particular solution of that differential equation. This solution was the general solution equation of the differential equation, and now when we have particular value of the a and b and we put these value of a and b in this equation, we will get the particular solution of that differential equation. So let us obtain that particular solution. So at the place of a, we have written the value from the equation 27 for a. This is a, and you now know a cos root ks, and this is the value of b. So this is b sine root ks. So in our solution of differential equation, we have inserted the values of a and b in the form of initial condition. So now this x is as a function of initial condition and magnetic strength K here in this equation. Similarly, we will get x prime also. Here you can see this is the again A, and this is the value of the B. So now what we can do, we can collect the term of x0 together. So you will get x0, and inside bracket you will get cos root ks0 cos root ks plus sine root ks0 sine root ks. Means you will get x0 cos and root ks minus s0. Similarly, when we will collect a term containing x0 prime, you will get such kind of trigonometric formulation there also. Similarly for the x prime. So finally what we will get? We will get x0 cos root ks minus s0 plus x0 prime root k sine root ks minus s0. This is our final solution. Means x at s as a function of initial coordinates x0, x0 prime and magnetic strength k. Now if this s, suppose this s0 is our beginning point of the magnet. If s is at the end point of the magnet, then this s minus s0 is actually the effective length of the magnet. And in that condition, these x and x prime will be the coordinate of the particle trajectory at the end of the magnet. So we have obtained the coordinates of the particle trajectory which is passing through the magnet if we know the initial coordinates. Means if we know initial state of the motion of the particle, we get the final state of the motion of that particle using these solutions. So now you can see from here, this we can write down x is equal to x0 and some term related with cos plus x0 prime and some term related with sine, and similarly x prime is equal to x0 with some term related with sine, you can say 2, and plus x0 prime with some related to 0. So these solution can be written down in the matrix form which is written here, and the element of the matrix are cos root kl 1 upon root k sine root kl and minus root k sine root kl and cos root kl. Here you can see that the second row of this matrix is basically the differentiation of the first row, and this should be because we have x and x prime. X prime is the differentiation of the x, so second row should be the differentiation of the first row. And in this manner, if we know the initial coordinates of the particle, we can get the final coordinates. Here this solution is most general. Most general means we have obtained the solution in terms of k, and we have seen that for different magnets k has different values. For dipole magnet it has 1 by rho square. For quadrupole magnet it is just the gradient normalized by the magnetic rigidity, and in the case of drift space k is 0. So if we will put these particular values in this matrix, we will get the matrix of that particular element. So we will obtain now matrices particularly for drift space, quadrupole magnet, dipole magnet, and one another type of magnet which is known as wedge magnet. What is that wedge magnet? We will come to that point.